Regression exercises. In this program, we'll look at some exercises using both simple and multiple linear regression. We'll focus on checking the significance of the regression model, and if significant, using that model with our prediction and confidence intervals to make some simple estimates. Let's begin by looking at some new data. Variables 1 and 2 show an accounting problem. The accounting firm is trying to see if the amount of assets is a good predictor of long-term debt. So the first thing that we would like to do to examine that relationship is use our scatter plot to see if there is a linear relationship between assets and long-term debt. We see that there is a linear relationship and that it is very strong. We can see that R equals 0.9218. Our R-squared value is about 85%, which shows that about 85% of the variation or change in long-term debt for a client can be explained by the amount of assets that that client holds. Now we need to check the significance of this regression before we can decide to use it. Looking at our t-test for slope, we could see in this case t for 10 degrees of freedom is a very strong 7.52, which corresponds to a p-value very close to 0. So in fact, there's a highly significant linear relationship between assets and long-term debt. So what does that mean? It means that this is probably a true linear relationship. In other words, beyond the sample of clients that we see here, which is relatively small, the relationship is probably going to hold for the entire population of clients. So we will see this relationship between assets and long-term debt. Because it's a true relationship, we can use this linear regression equation, y hat equals 0.8121 times client assets minus 7.84. For example, if a client has 50 million in assets, our data here are in millions, the regression equation predicts long-term debt of 32.77 million. So suppose this accounting firm has a client with total assets of 50 million. Let's construct a 95% interval estimate that will produce a range to estimate the amount of long-term debt. Because after all, the 32.77 is just the point on the regression line directly above 50. We know that in reality, all clients who have 50 million in assets are not going to have exactly that amount of debt. So we have two interval estimate tools, our confidence interval and our prediction interval. And they're both intervals that are built around our y hat. The only difference is the margin of error. The confidence interval estimates the average long-term debt for all clients who have 50 million in assets. But if the accounting firm is interested in a particular client, they're going to want to use the prediction interval. A particular client at 95% confidence should have long-term debt somewhere in the much wider range, 22.83 up to 42.71. Before we can really decide that this is a good regression model, we should check our residual plot. Remember, linear regression assumes a normal distribution of residuals and most importantly, constant variation of residuals. So remember, if we have that approximate box-like shape on our residual plot, in other words, we don't see any clear drift, we can decide that the regression model meets those model assumptions and is indeed indicative of a true linear relationship. Let's try another simple linear regression exercise. Remember, our emphasis is on checking the significance of the regression model and most importantly, using the model to make some estimates. That's how we really want to use our regression models. So the next problem concerns variables 3 and 4, and this is actually an IRS data set. Here we have a sample of AGI, or adjusted gross income, for particular IRS tax returns. And we also have the amount of charitable contributions in dollars. So our AGI is in thousands of dollars, and the charitable contributions are in dollars. So the IRS would like to model the relationship between AGI and charitable contributions. And there are several reasons to do this, such as tax auditing. But before the model can be used, we need to check to see that in fact there is a linear relationship between AGI and charitable contributions. And our strong correlation, very strong at 0.96, and our scatter plot as well, shows pretty clearly that there is a strong linear relationship. In fact, the regression equation can explain over 92% of the variation in charitable contributions. So the regression equation of y hat equals 195.7, we'll say, times AGI minus 6,169 and 94 cents is what we would use to make our predictions. For example, if AGI is 70, the regression equation forecasts or estimates a charitable contribution level of 7,528 and 95 cents. Now, the IRS could use this in a number of ways. But before doing so, we would of course want to check our significance results, and the very strong t-stat and the very strong p-value near 0, as well as our confidence interval for beta 1 clearly excludes 0. So these results are telling us that there is a true linear relationship between AGI and charitable contributions, one that should hold throughout the population of IRS tax returns that include charitable contributions. So how might the IRS use this model? Well, let's consider a use for the audit risk, assessing that risk for a particular return that has charitable contributions. So if I file a tax return with an AGI of 70,000 and my charitable contributions are outside of the range of the interval, and specifically if they are above the upper limit in our interval, this would indicate to the IRS that maybe this is an inordinate amount of charitable contributions given an AGI of only 70. In a more general way, the IRS could say, on the average, any return with an AGI of 70 should not have more than about 8,300 in charitable contributions. And so very quickly, returns that do have charitable contributions outside of that range could be flagged for a higher audit risk. So far, we're seeing that regression modeling has clear, useful application to business statistics because it allows for us to apply some science to making some predictions or estimates about an outcome or response variable, what we call the dependent variable, given something that we know, such as assets or AGI. Now, the multiple linear regression has even more application to business because frequently in business, our key outcome variables are affected by more than one independent variable. So in theory, if we have more than one independent variable, we would expect to be able to explain even more of the variability in our dependent variable. And that's the case here in this application of multiple regression, and our data are here in variables 5, 6, 7, 8, and 9. This is a car dealership problem, and the owner of this car dealership sells only vintage Corvettes. And he would like to develop a forecasting model using regression to determine the price range for a particular Corvette that he is selling. So, of course, he has the mileage of each of the cars that he's selling, and he knows the year of the cars that he's selling. T-tops or some sort of a removable roof is also something that he's considering as having a possible effect on price. So price, quite clearly, would be the dependent variable. That's the variable that this owner of the Corvette dealership is trying to predict. And variable 9 is what we call a quadratic adjustment. This is the year squared. And even though that doesn't seem to make a lot of sense, we're going to take a quick look at how we might use that type of an adjustment. So first of all, let's set up a multiple regression using x1 and x2, where x1 is mileage and x2 is the year. So our independent variables would be number 5 and number 6 on our data sheet, and the dependent variable would be price. A quick check of the multiple regression data confirms that we are actually using the data that we intend. So now let's look at our results. First of all, remember that when we are trying to get a percentage of explained variability, if we have more than one independent variable, such as we do here, mileage and year, we would use the adjusted R-squared. And the reason for this is adding more independent variables tends to increase R-squared. And so the adjusted R-squared corrects for some of that R-squared value that's due to the number, only to the number of independent variables. So 82% approximately of the change in price can be explained by mileage and the year. Now, looking at our p-values, we can see that according to the high p-value of 61.6% for year, when mileage and year are together, year maybe is not contributing much explanatory power to our model to forecast price. And we could speculate as to why. Looking at the correlation matrix, we see that there is a very strong negative correlation between mileage and year. And we would expect this. The older cars should have more miles. But as the year increases, that is, the car is newer, we would expect there to be fewer miles. And in fact, that linear relationship is very strong. So mileage and year, we would say, are collinear variables. And the p-value is indicating to us that all of the explanatory power that we would get from the year of the Corvette, we're already getting from the mileage of the Corvette. But for now, let's leave mileage and year together and see if there's any change to those results by adding X3. This is our removable top, or T-top. And you can see that we've created an indicator variable, or what we sometimes call a binary variable. The ones are Corvettes that have that removable top, and the 0, of course, Corvettes that do not. So variable 7 would be an X3 on this multiple regression model. And we can see that it is statistically significant, at least while year is still on the model. And we can also see that there's no strong correlation between T-tops and mileage. In fact, it is very, very weak, as well as the correlation between T-tops and year is very, very weak. So now let's see if we can correct this model stepwise. So remember, stepwise multiple regression involves locating any variable that has a p-value over 5%. And if it's the greatest p-value, the largest, above 5%, that would be the first one that we would consider deleting from the model. So let's do that. If we remove variable 6, which is the year, we would also want to move up T-tops to the variable 2 position. Let's check our results. Okay, well, we improved our adjusted R-squared by adding the T-top variable to the model. We were at about 82%, and we went up to about 87.7%, or nearly 88%. Also, removing year did not affect the p-value in terms of significance for the T-tops. It stayed very close to the same value. So what kind of an effect does the T-top variable have in dollars on the price of a Corvette? And we could answer that question by looking at the slope. The rate of change is $2,886 and about 84 cents. So if a Corvette has that removable roof, we would expect the price to go up on average $2,886 and change. And we could see that reflected then in our confidence and prediction intervals. So when we make forecasts, it's best to stay within the range of the available data. Okay, so the lowest mileage that we have here is about 15,000. And the greatest is about 125,000. So in theory, we could estimate the price of any Corvette within that wide range of mileage. However, Corvettes that have fewer than 15,000 miles or greater than 125,000 miles, we don't know anything about the effect on price. We could speculate based on what we're seeing with these data, but we simply do not know. And so we would avoid making forecasts with X values outside of the range of X data. In fact, when we do go outside of the range, this is something called extrapolation. And it's something that with a linear regression model of this type, we would want to avoid. So let's make some estimates. We know our range of mileage. Let's say if a Corvette has 75,000 miles and it does not have a removable roof. We can see the y-hat values. Those are always going to be the same. But the margin of error for the two different interval estimates, that's where we see the difference. So if we were trying to estimate the price of a particular Corvette that has 75,000 miles and no removable roof, we would estimate at 95% confidence that the selling price is going to be somewhere in this range, 10,039 and change up to 20,926. But as a seller, we might be concerned more with the average selling price, assuming that we might sell several of these types of Corvette. So on the average, at 95% confidence, we would estimate the selling price, the average selling price, to be somewhere in the much narrower range, 13,558 up to 17,407. So let's see that effect of T-tops. What if we had the same mileage, but we did have a removable roof of some sort? We would simply change our indicator variable to 1. And we could see the effect. So it is sizable. And we can see that in our data. And that is reflected in our interval estimates. Before getting too attached to this model, we would want to consider any strong outliers on our residual plot or any clear drift. Now we do have one rather large residual here that we can see. But we don't have any clear drift, and let's see if that one is strong enough to be an outlier. That would be here, and it only has a standardized value of 2.062. So the model seems to be okay, satisfying those required model assumptions and relatively free of any regression outliers. Now, we've already established that the multiple regression model using mileage and T-top as independent variables is a pretty good model. It seems to satisfy the assumptions. It has an adjusted R-squared, about 88%, and both independent variables are statistically significant. We also saw that when we had the variable 6, year, with those two, mileage and T-tops, that year was quite insignificant. For example, this is a previous version of our model, and we saw that year had a p-value well over 5%. Now, this has to do with the way year is fitting the model. And we could explore that further by looking at a simple regression, trying to isolate the effect of year on price, or that relationship. So looking at our scatter plot, we see clearly by the correlation that there is a linear relationship. We could also see from our significance results that the p-value is quite strong. So why isn't it working on our model? Well, it could be because of what we see here. We see somewhat of a curved pattern in the data. And we could correct for that by using a quadratic adjustment. The quadratic adjustment would be the year squared. And that's what we've added here. So whatever the quantitative variable is, if we wanted to use a quadratic adjustment, we would square that independent variable and then use both. Okay? So I'm going to add the variable number 9, our quadratic adjustment, to our multiple regression. And let's see what happens. We can get rid of those. Well, our adjusted R squared is now over 96%. But remember, we had problems with the significance of the variable year. However, adding that quadratic to the model has corrected some of that, and now these variables seem to be the strongest variables. We still would be cautious about the collinearity, but not here. The correlation between year and year squared, we would expect to see that, and when we use a quadratic adjustment, we would not be concerned about that. But if we wanted to, or perhaps for operational reasons, needed to use the year along with mileage and t-tops, this would be the way to do it. And therefore, when we have those variables successfully added to our model, we would be able to make forecasts of price using all 3 independent variables as well as the year squared. Looking at our residual plot, we don't see any flagged standardized residuals, and therefore we can conclude that the regression is relatively outlier free. And while we don't see a perfect residual plot by any means, we also don't see any clear or systematic drift. This concludes the program Regression Exercises.